So we're going to look at another example. We're going to look at a car going over a hill. Okay, so as a car goes over a hill, we want to look at what's happening. Well, the car is going up here, going down on that side, so there has to be a downward acceleration on here because we have an upward velocity on the left, a downward velocity on the right. Okay, so we look at it and say, well, right near the top here, there has to be a centripetal acceleration because we can imagine that this hill is like a fraction of a circle with a radius of curvature r. That means there has to be, at the top of the hill up here, if the car is going over, a centripetal force. Well, we know that gravity is pulling down, but the normal force is pushing up. Now, when the car is on level ground, then mg is down, normal force is up, and so that means that the normal is going to be equal to mg. Now, if it's going over a hill, it's a little bit different because now we know that there's got to be centripetal force. So the centripetal force is mv squared over r. That's a downward force. Well, what's pulling down? Well, mg is pulling down and the normal force is pushing up. So mv squared over r equals mg minus fn. Okay. So mv squared over r equals mg minus fn for a car that's driving over a hill. Well, that means the normal force equals mg minus mv squared over r. And so, well, what does that mean? Well, that means that the normal force is how you experience weight. So that means if you're going over a hill, it's as if you weigh less. Okay. And if you're in a dip and driving, it's going to be the plus sign is going to be as if you weigh more. And this is actually measurable. So in other words, if you're standing on a scale, say that you're in a bus and you're standing on a scale, okay, if it's level, the scale reads mg, it reads your weight. On the top of a hill, it's going to read less than your weight. So it looks like you lost weight. On the trough down here, on the dip, it's going to weigh more, so it's as if you gained weight. Well, as you go over the hill here, then what happens is that you have the normal equals mg minus mv squared over r. Well, the faster you go, the bigger the v. Eventually, you reach a point where the normal is 0. Okay, so that gives you the maximum velocity. Okay, because you don't want the normal to go negative. So that means that the maximum velocity you can go over, well, we just do some algebra here, mv squared over r equals mg, the m's cancel, so the maximum velocity is going to be the square root rg. So that if you try to go faster than that, what happens is the normal, instead of going negative, just is not big enough. In other words, mg is not big enough to keep you going, and so you launch off the hill and land somewhere else. This was a perfect example of this, was where Harwood crossed precinct line. So about 20-something years ago, they redid the road and they changed it. But used to, cars driving down Harwood, when they got to precinct line, the maximum velocity, because the curvature of the road was so much, the maximum velocity was actually less than the speed limit. So if a car was crossing at the speed limit, they would become airborne and impact the ground just beyond, on Harwood, just beyond precinct line. And there were all these gouges in the pavement there where that happened. And then often little car parts now and then. And so now, good engineer, civil engineer, would have this in mind so that the road curvature would not exceed that particular value. Well, once again, engineering. Suppose you want to control the speed. So, for example, you've got a neighborhood and you want to slow cars going in the neighborhood. So you put a hump in the road. and that hump is like a fraction of a circle and has some kind of radius. And what you want to do is control it so that the maximum velocity that's safe to go over is going to be equal to 25 miles per hour. Now, that's what we call a road hump, if it's 25 or 30 miles per hour. A speed bump is actually something you find in a parking lot, and a speed bump normally has a maximum speed of like 5 to 10 miles an hour. But a road hump is a little gentler sort of thing that just limits you to not going too terribly fast. And so we say, well, okay, so we know that mv squared over r, if you're at max, then this is going to be mg minus the normal. So at maximum, the normal is 0. So the m's cancel. So r is going to be v squared over g. Well, 25 miles per hour, we got to do unit conversions. So 36.7 feet per second. G is 32.2 feet per second squared. Remember, if we're doing feet here, we got to do feet there. So R, v squared over g, turns out to be 41.8 feet. And so that is the radius of curvature of a road hump designed to keep you at or below 25 miles per hour. Okay, so that's what you design it for. So again, this would be something a civil engineer would have to design or figure out if you want to do it right. Often these things aren't really done right. They just have someone like throw it out there and say, "Oh, okay." But really, if it's done properly, an engineer should be involved and should actually figure out really what it should be. Well, interesting thing, you've got this right here going over. If you're going too fast, you launch off. Well, over at Six Flags, they actually have roller coaster cars that are designed to exceed that maximum velocity. So what keeps them from going off? Well, we know that mg is pulling down, okay? We know that mv squared over r is supposed to be down, but if mg is not big enough to be equal to mv squared over r, there has to be something else. There has to be another normal. So in other words, there has to be a normal pulling down in addition to the mg. Well, how do you get a normal down? Doesn't the normal go on the opposite direction of the surface? Well, what they do is the roller coaster has wheels on the bottom of the coaster rail also. So over here, where you're going up the hill, the top wheels are riding on the rail. When you're going across the top, the bottom wheels are holding you onto the rail. Okay, now the problem there is you got the passengers in here, and so the passengers, if the car goes over, the passengers want to just keep going like that, and what keeps them in is the lap bar. When you go look at the roller coaster, there's a sign that says you have to be this tall to ride the roller coaster. There's always a kid or two that's just a little bit shorter, and they're trying to stay on tiptoes, say, "I'm that tall, I'm that tall," and they're not supposed to be allowed to get on there. The reason you have to be a certain size to ride the roller coaster is if you're not the right size, the lap bar doesn't hold you into position, and so then you go launching off. Or if you're too wide, the lap bar doesn't hold you in, or something. So it has to be done properly, and otherwise you can't. Otherwise it's not safe. And there have been a few instances where passengers have been ejected from the carts. Also at Six Flags, often as the car goes over, anything in the pocket like cell phones or glasses or whatever go flying off, and so there's usually right past where it dives over like this, down the grass, there's like a whole bunch of stuff sitting out there from riders all day, and the crew doesn't just stand down there and collect it, because they could get hit by more stuff. So what they do is like once a day or once or twice a day, they when the roller coaster's not running, they run out here and collect all the stuff, and so you have to claim it like the next day or something. And so hopefully it's not your car keys. But that is the basics of going over a hill and centripetal force. So you had, like, in this video we had like three different sort of things. We had the basic theory behind it. We had the idea of a civil engineer designing a road surface so that cars going the speed limit don't launch off the road surface if it curves over too sharply, and the idea of an engineer designing a road hump that has the right curvature to it to limit speeds to the level that you want it to be limited to. Uh, and then finally we have this idea of a roller coaster. So this is going over a hill, and then how centripetal force acts on all of that.